So I hope you can hear me. I would like to discuss a little bit about benchmarking, or how to benchmark maybe different heat pump architectures today. This is one. I'm just trying to get to the next slide. Yeah, there it is. So first, before I start on this, I would like to introduce my company, SynErgy Thermal Management, a little bit. Shortly discuss a cooperation we recently started with the American company Thermotech, who offer components, so we can also use vertical integration of their components in our projects. And then finally we get to the heat pump architecture benchmark. So my company was founded in 2016, so we're almost 10 years old now. I'm the owner and managing director. A long time ago, in the 90s of the last century, I would say, I studied mechanical engineering in Aachen at the University of Technology and specialized there in thermal engineering, heat transfer technology. Since then, I've been working for more than 25 years in the automotive industry on heat pump systems as, let's say, auxiliary heaters for diesel engines in the beginning, but later also for electrical vehicles with natural refrigerants, mainly CO2. We looked a lot into, let's say, how to get the complete heating performance down to minus 20 degrees ambient temperature available. And this led in the end to 2 serial projects that my team supported on the supplier side at that time when I was employed at Harnan Systems. Those were the Volkswagen e-Golf and the BMW i3 vehicle. So those heat pump systems that went into production in 2013, there is a bit of my, let's say, DNA in that. In 2016, then I started up my own company. I've been working on similar projects since then, but my customers have changed a little bit, let's say, from the large OEMs who have their supplier usually doing this work for this, to smaller companies. I had 2 thermal management development projects. One was for Sono Motors here in Munich. As most people here know, that they didn't make it, at least not on the vehicle development side. They still have the company alive, but only looking into the solar panels. And a similar story in the Netherlands, in Eindhoven or in Helmond, a company called Lightyear that developed a solar vehicle. I also was, say, responsible for the heat pump systems development in that vehicle. Apart from that, now I'm looking more into, let's say, other mobile applications like heavy-duty trucks or buses that are being electrified, and also construction equipment. There's a lot of activities going on there. So it's not only the passenger car market anymore. So independent, let's say, from the development activities, we recently started a cooperation with Thermotech. Thermotech is a HVAC and heat exchanger supplier in the US, and also have some manufacturing plants all over the world on different companies in, let's say, they delivering components to defense, also to bus, truck, and construction equipment area. So if there's any interest there in that direction, we can also support this, let's say, the development activities up to a prototype level, or even together with Thermotech into serial production. Now we're getting to the topic of the presentation. So yeah, benchmark, what is the motivation for a benchmark? I think every company that is developing something needs to look what is the competitor, or what are the competitors doing. Are there any trends in the industry that we need to look into? If you're looking into heat pump systems for electrical vehicles, we've seen since, let's say, the first heat pump systems in the late 2000s or 2010 around came into production, that nowadays most OEMs offer heat pump systems as an optional choice. And we see also that the take rate of those heat pump systems is more than 50% in most cases, at least in Europe. So it's a topic that is present at all OEMs, and yeah, we're looking into that. Apart from the heat pump system itself, there are also some new requirements. The fast charging is putting a very tough requirement on the refrigerant system. We need to provide more cooling performance, let's say, during fast charging than you will ever need during normal vehicle operation, and that, let's say, in a condition where the vehicle is not driving, you need to get rid of the waste heat in the condenser or gas cooler for a CO2 system under conditions that you don't have much airflow there. So that's a tough requirement. And if you look on the battery thermal management, so apart from the cabin, also the battery needs to be managed. And the state of the art at the moment, at least, is let's say coolant-cooled batteries, and then like the colleague from Webasto explained before, then the chiller who is cooling down the coolant at higher ambient temperatures. So those are, let's say, the most common architectures in general, but in the details there are, of course, several differences. Some older systems were using orifices or TXVs as expansion organs, so that you don't have any means to control it, and that led usually to a situation that at negative ambient temperatures the system was shut off, and you need electrical heater to heat up the cabin. Nowadays we see that, let's say, there are one or more externally controlled expansion valves in such a system, so that you're also able to control the refrigerant flow and the temperature levels in each heat exchanger and the way you would like to have it, and to have it optimal, so that you're able to operate your system also at minus ambient temperatures. And another trend, of course, is the modules that are being built to save cost, to put together some components in modules or subsystems. On the benchmarking side, what our objective here was mainly not to, let's say, test existing vehicles and compare them, because in each vehicle you have, let's say, package restraints which may lead to a smaller heat exchanger that is the bottleneck for a certain system performance, or if you have a vehicle that was a big issue in the VW MEB in the first vehicles, the control software was not working properly, there were some bugs that had to be fixed. So if you test a vehicle on that design level or that serial production level, you get a very bad result. But if you would have a vehicle that, let's say, has an update half a year later, you would get very different results. So we looked more on the, let's say, ideal operation, or with physical constraints, of course, so not ideal in terms of not realistic, but how would we control a heat pump system that you get the best COP and achieve the performance that is required for those operating conditions. And for that, we basically designed in a virtual environment the components. So we have component models, system models, and then compared to different architectures, all with the same components that are able to achieve the, let's say, cooling performance targets. And in case the heating targets at low ambient temperatures are not achieved, we add additional electrical heating to get to the same performance. Because it is, of course, not easy to compare a system that has a bit more performance but uses a lot more energy. You want to have the same performance and then say this is more efficient because it uses less energy in the operation. So boundary conditions we used for this are an industry standard, so-called SIE matrix, that is, let's say, used by all OEMs worldwide. It consists of over more than 60 operating conditions from minus 40 degrees ambient temperature up to plus 40 or 45 degrees. They represent also, let's say, cold start conditions, partial heat ups or partial cool downs, and steady state conditions. And each of these points were simulated then with the system architectures that we looked into. In passenger car application, the heat pump performance is, let's say, in a lot of cases limited to the heat source. If you don't have any waste heat available in the cold start condition, you can only use ambient air as a heat source. You cannot use this, let's say, unlimited, because you would freeze up the evaporator. So we are controlling in our system models here this in a way that we don't freeze. So this would be a continuous possible operation under these conditions. And in case we don't achieve the required heating performance, we add electrical energy in the airflow to get to the desired air out temperature on the HVAC. So what are the architectures we benchmarked? So we basically looked into all available vehicles that have a heat pump and the information we could get on an open source level. Also, we are not using any confidential level information from specific customer projects, but there are a lot of, let's say, forums, manuals, maintenance manuals from the OEMs where the architectures are described. videos from Monroe, which are online available. So with this, we drew up the architectures. We have in total, I don't know, something like 15 vehicle architectures in here. And for each architecture, we design or basically draw up the operating mode for cabin cooling, for cabin heating, for reheat conditions, combinations with battery cooling or battery heating in case this is required, and then simulate under the different ambient temperatures from that SAE matrix what is the power consumption for this condition. And we also look a little bit into specific design innovations. Of course, everybody knows in Tesla the octovalve and other module buildings. There's a lot of information on that available, but we summarize this also for some less known vehicles. And then, let's say we get to the more detailed conditions that are, let's say, interesting for our operation. So if you look on operating limits, we have, of course, on the heat pump side, suction pressure and normally automotive compressors are not hermetic, so you're not allowed to go below 1 bar absolute pressure to prevent that air can permeate into the refrigerant system, and with air also humidity, and this could lead then to damage on the compressor over time or reduce the durability of the compressor. There's a discharge pressure limit that is depending on the refrigerant that you're using. So in the benchmark there is a CO2 system, which has of course higher suction pressure and discharge pressure limits. The compression ratio, all of these systems are using scroll compressors, which have a limitation on the compressor ratio, compression ratio. You can't have ratios of 20, 25. So if you have a YF system and operate it at minus 20 degrees ambient temperature as an air heat pump, you have a suction pressure slightly above 1 bar. But you would need to have 60 or 70 degrees on the air temperature, and you would need 22 bars on the high pressure side for that. A scroll compressor will not be able to realize that, at least not continuously. So those limits are in our simulation models. Also the discharge temperature, that is also a bit changing, of course, depending on the refrigerant. And then from the test conditions, which are described in this matrix from the OEMs, there's basically the available waste heat from the battery, from the powertrain that you're allowed to use, or in some cases you're not allowed to use it because the battery is not yet on temperature. And also, of course, the ambient air. So some architectures have ambient air as a heat source, some only have the waste heat, some have both, but there are also architectures that have the possibility to operate with both heat sources, but not at the same time, which is also sometimes an issue under some conditions, and that leads to very interesting results in the end. If you look, for example, on the ambient air as a heat source, like I said before, we are controlling this in a way that we can operate continuously so that the ambient heat exchanger does not ice up. And in the end, let's say if we have a sufficient high airflow through the heat exchanger and a low temperature difference, those are the main, let's say, influence factors there, we are able to operate this continuously. This is, let's say, all based on a patent that is publicly known, so this is not that's published, so you can look into that, or I can name you the number if you have interest about that. And if you control your system in the wrong way, you would get a situation like is shown here. So the blue line that you can see here, that is basically the ambient temperature. The compressor control controls basically the outlet pressure, which would be in case of if you don't have any superheat, the saturation temperature, which is a few degrees, let's say maximum 5 degrees below that ambient temperature. But if you have a very high mass flow, you have also a lot of pressure drop, and unfortunately in the refrigerant has, let's say, a temperature change that is based on a pressure change in the two-phase area. Those two physical conditions are connected. So if you have a high pressure drop, that could lead to that you have in a certain area of your heat exchanger a temperature that is higher than ambient temperature. So first you waste heat to the ambient, and then you have a smaller surface left to pick up heat, which is of course very inefficient. So it's necessary to control it in a way that this temperature is always below ambient. on the other side, if you let's say, have a control that is causing too much superheat, you are measuring your temperature on the outlet of the heat exchanger, think everything is fine. You can also have a pressure or temperature sensing on the inlet that you control, and also here you are fine, but because of the superheating, you have a lower saturation temperature on a part of the heat exchanger, and in this area that is below, let's say that 5 Kelvin gap, for example, your heat exchanger would ice up, and this will grow over time on a total heat exchanger surface because you reduce the heat that you can pick up. If you do it the right way, you have a very small superheat, and your refrigerant temperature is always below, let's say, the ambient temperature over the complete surface of the heat exchanger. Why do I show this here? Because this characteristic on how this line drops is depending on the refrigerant. So if we have, let's say, a temperature difference of 5 degrees that we are allowing for YF or 134A, that means only half a bar pressure drop. But for a C2 system, half a bar pressure drop is only 0.5 Kelvin. So you can allow a much higher airflow, much higher refrigerant flow through the heat exchanger with CO2, allow a much higher pressure drop, or you have a lower temperature on the inlet and you have a higher delta T over the complete surface of the heat exchanger, and you can pick up more heat from the ambient air without icing under the same conditions. So therefore, a CO2 system has a big advantage when you use it as an air heat pump compared to a YF system. Somehow this is not working. Somehow it does not go to the next slide. There it is. So if you look on the conditions that we are simulating, let's say there are other factors in there, but let's say the main impacts are the ambient temperature. So we have, let's say, in the range from -40 to +45 degrees. There are more than 60 conditions in total, and there are also occurrences, how often each operating condition, which is, let's say, not only the ambient temperature, but for each ambient temperature is also like a startup, partially conditioned and a steady state condition. So this leads to an occurrence, and this is all, let's say, agreed in the industry as state of the art. So this is an occurrence for a North American climate because this is an SRE matrix. So for each condition that we simulate, we have a power consumption, we have a heating and cooling performance we achieve, which are all on the same level because else we can't compare the efficiencies or the power consumptions. And if you multiply, let's say, the conditions with the operating time and these occurrences, then we have something like a yearly energy consumption. So we can compare basically how the yearly energy consumption of a certain architecture would be, and compare these and say this architecture is more efficient overall in the year, or we can also look into heating, cooling, or reheat cases to look a little bit more into detail. So if we look, for example, here on the heating cases, I just zoomed in a little bit, so we have a few points with -40 degrees ambient temperature. This is also for a CO2 system too low, you can't operate it there, you would be below the allowed suction pressure for a C2 system. That's not 1 bar, but it's a little bit higher because you would get dry ice, and the compressor also does not like that. So the -40 degrees can only be reached with an electrical heater. So I totally agree to Michael from Webasto from the last presentation. If you have these conditions, I've never been myself driving at -40 degrees ambient temperature, not even on test drives in the Arctic area, but if that would be the case, no heat pump would be working. So -30 degrees, there already it looks a little bit different. So we have a CO2 system that is available to, in steady state, that is this condition, to achieve the total required heating performance under those conditions without any additional electrical heating. Not in the cold start, of course, and there the required condition is not met, so either you are taking longer to heat up or you need to precondition, but in steady state you would be able to deal with the CO2 system alone. If you're looking on the other conditions, so the other heat pumps that we have in here at -20 degrees, then let's say also other heat pumps start working with YF as a refrigerant, but not all, oops, sorry, to go back. not all achieve the required heating performance. So in this case, let's say this gap between these systems here and the target of the black curve would need to be compensated by electrical heating. If we then look a little bit into heating, cooling, and especially also the reheat cases, we also see some interesting thoughts. So we have in the heating cases, where it is? In the heating cases here, I think the battery is almost empty. So on the left side, on the heating cases, the yellow bar, that's the CO2 system shown before. So because we have a higher heating performance, this is using less, let's say, power from the battery to heat up the cabin and the battery compared to a YF system or a system that does not have a heat pump, which needs to provide this all electrically. But maybe just go back one step. So the occurrence of those very cold temperatures is, of course, very, very low. So in the yearly energy consumption, that's not a big impact. But during all heating cases, the CO2 system is just more efficient. On the cooling conditions, we see, so in the third set of columns here, that there are also some differences. This is mainly due to, let's say, the CO2 system has a little bit lower efficiency at the very high ambient temperatures. That's also well known. They are also not that often occurring in that table, but they are there. And let's say systems that have a liquid cool condenser also have, of course, some disadvantage there because the high pressure is higher. And that orange that is a bit lower, that is a system with a pure direct condenser that is the most efficient there. Interesting is the middle part of the first three columns, so the second set of columns, that's the reheat condition. In reheat, we are cooling down the air to dehumidify it. The air is too cold, and then in the end, we need to heat it up again to get to comfort in the car. And the most right column, that's a system that has no heat pump, that needs, let's say, compressor power consumption to dehumidify, and then needs electrical power consumption to reheat. There are other systems that are not able to, let's say, provide the complete heating performance with the heat pump. They're also a bit higher on the level, and let's say a well-designed heat pump system that can operate on different pressure levels and can control them with externally controlled valves is able to provide both the cooling and the heating performance as required without additional heating from the electrical side. And the most right set of columns, that's the total energy consumption over the years. So we see here also some big difference in some heat pump systems that, let's say, are not able to always operate the heat pump system in the most efficient way, mainly due to the orifices or TXVs, or if they are not able to provide heating performance, that they have to add electrical performance or use a short cycle, which is also less efficient than electrical heating in the end. So that is what leads to these results. On the next slide, I also put together some other information. So we have in the benchmark, we can also look into cost, complexity, maybe some other topics that the customer might find interesting, and we can weigh these parts. So the efficiency is not the only topic, but of course, if you have lots of expensive valves, the system gets more expensive, and if you have maybe a small car, that's not that interesting. So you can weigh basically the comparison on the cost, on the efficiency, also on some other topics, and then in the end you can support our customers in this case with what would be the best architecture for their purpose. And yeah, with that, on the next slide, I would like to sum up basically. So we have a benchmark that allows the comparison of architectures, so not without any influence of component design or, let's say, good or bad control of the refrigerant system. We are able to compare performance, efficiency at the same performance, power consumption, cost, and other feature content. So maybe for some customers not important to have fast charging. If he does not weigh this very high, then the architecture can look different than in case that is a very important part for him. The use cases we have shown here are automotive standards, but of course they can be adapted to whatever the customer needs. And also the weighing factors can be adapted for different purposes. If you have a city car or, let's say, a HEV or sports car or some SUV. That might be different objectives or different weighing of cost and efficiency. And yeah, our objective is to support the OEMs and the system suppliers in defining their own architecture and to find out what is, let's say, something that is worthwhile looking into, and maybe some parts that are very expensive or complex that can be left out, to find out with support of this benchmark. Of course, we have the benchmark report available. We can adapt this also to specific customer needs, and we can also provide the 1D simulation models for that. And if there are any questions, I'll be glad to answer them.